Now, good morning, learners, and welcome to my second lesson on atomic structure and periodic table. In my first lesson, I did mention about basically the atomic structure, and I think we mentioned here that an atom basically contains the nucleus. It contains the other part, or the part outside the nucleus, which basically will be formed or comprises of the energy levels. And we actually mentioned here that the electrons are found in this region or where we have the energy levels. And I remember having said here that every time you're drawing or you're presenting an atomic structure, every time you're drawing an atomic structure, you've got to have the protons, and not the protons, but you've got to have the nucleus. And in this nucleus here, it's important to mention the protons that are there and the neutrons that are there. And then finally, you've got to have the energy levels, which are basically will surround the nucleus. That is what we actually talked about. Now, in today's lesson here, I'll be taking you through some terms that we use in when we're talking about the atoms. And the first term here is the atomic number. We're going to look at it there. We have the mass number. And then we may also look at maybe the representation of an atom, and at the end of the day, or maybe at the end of the lesson here, we're going to look at the isotopes. Now let's start by defining atomic number. Now atomic number here, it is the number of protons. It refers to the number of protons in the nucleus of an atom. It refers to the number of protons in the nucleus of an atom. Now, one important thing about the atomic number here, atomic number is actually the one that defines an element. Now, every single element here will have the same, or the atoms in an element. The atoms in an element here will have the same number of protons. The same number of protons. In other words, they will have the same number they will have the same atomic number. They will have the same atomic number. Therefore, this one is very important here. I think it's more important to note that. It is very much important because it defines an element. If I talk about, for example, the hydrogen has atomic number 1 there, if helium, lithium, number 3, beryllium, atomic number 4, like that. We're going to look at it. Now, then the other thing that the other unit that we use here is the mass number. It is the mass number. Now, mass number here, which we maybe can abbreviate it here with an A here, refers to the sum of protons. Therefore, protons plus neutrons. Protons plus neutrons. Remember the two here, we also called them we call them neutrons because these are particles that we find, or they are actually found in the nucleus. They are found in the nucleus there. So therefore the mass number here may be abbreviated as A here. It will be equal to protons plus neutrons. Remember, still in chapter 1 I mentioned here that the mass of an atom is concentrated in the nucleus. Why did we say this? Because the protons and the neutrons have a mass. They do have the mass. Remember, the electrons we mentioned here, that they have negligible mass. They have negligible mass. So basically that is what we're talking about as far as the mass number is concerned. Maybe it's also important to mention here. There are times we can have an element here. We can have an element with atoms with the same atomic number. In other words, the atoms have the same number of protons. But because of a difference in the number of neutrons, here, then what happens here is the mass number may change. The mass number may change. Now, those kind of atoms with the same atomic number but different number of neutrons, we'll be calling them isotopes. Isotopes. Now, let me mention about how do we represent an atom. how do we represent an atom, a representation of an atom here? Now, an atom may be represented. An atom may be represented here using the atomic number and a mass number, and of course the chemical symbol. The chemical symbol. Basically, that's how we are going to represent an atom. Now, maybe what we can, what is maybe new here is how are we going to do it? Now, basically, how we're going to do it here, the mass number. Let me use A to present the mass number here. The mass number will be written here on the top left of my symbol here. Now, let me talk about maybe a given symbol here, like W. W may not be a chemical symbol of any of the elements, but let me have it there, W, to represent any element. And then I'm going to have Z here. Now, the Z here actually represents, the Z represents the atomic number. The atomic number. So basically, this is what we're going to do here. That the mass number here will be, we are going to write it on the top left of my element W here. And then atomic number here will be bottom left of my element. Here, which is actually, I'm also going to present it using a chemical symbol. Now, let's talk about a specific element here. A specific element here. And I want to talk about something like sodium here. Now, sodium, we see here, sodium here will have 11 protons. It will have 12 neutrons. It will have 12 neutrons. And of course, 11 electrons. It's important to mention here that the number of protons and electrons are always equal. They're always equal in an atom. In an atom. Just get note of that. Now, if we were to present this here, we can present it like this here. The mass number of this atom here will be protons plus neutrons. This is 12 plus 11 here. Now this gives us a 23. That gives us a 23. Now the Z here, which also maybe present the atomic number. The atomic number here refers to the number of protons. The number of protons of my atom here, in this case, sodium here has 11 protons, and therefore the Z will be 11. And therefore, how do we represent? How do we represent the sodium element? How do we represent the sodium element? This is the way we are going to present it here. The mass number, of course, is a 23. The mass number is a 23. The atomic number here is an 11. The atomic number is an 11. And the chemical symbol of sodium here is Na. Look at that. 2311 Na. That's what we're talking about. And therefore here, if I'm going to have such a representation, you should be able to tell the mass number. You should be able to tell the atomic number. You should also be able to tell the neutrons and even the electrons and even the electrons. That's what we are talking about. That's what we're talking about. Maybe I can have maybe one question on this and see what we are exactly talking about. What we're talking about. Now, having discussed about the representation of an atom, maybe let's look at maybe a simple question that we can have from that, just to tell us whether we may be able to understand what you're talking about. Now, we have an atom here that has been represented as that is 717X. From what we just mentioned here, now the superscript here, the superscript of this here refers to the mass number. Now, the subscript here, which is 17 here, represents the atomic number. It represents the atomic number, and of course the number of protons. And of course our X here represents the chemical symbol of my element. The chemical symbol of my element. So let's maybe start with the Roman A, or I mean not Roman, but question A. And if the number, find the number of protons. Find the number of protons. Now we know that the atomic number here, atomic number is also equals to the protons here, the number of protons is equal to the number of protons, and therefore it will be equals to 17. It will be equals to 17. That is what we are talking about. That is what we are talking about. Therefore, the atomic number of that element will actually be 17. Now, talk about the number of neutrons. Talk about the number of neutrons. Now, we've just said here that the mass number which here we are given to be 37 here, should be equals to the number of protons, which is actually 17, the number of protons equals 17, plus the number of neutrons, plus the number of neutrons. Let's have that. So if that's the case there, therefore we can say that n will be equals to 37 minus 17, and therefore n will be equals to 20. N will be equals to, therefore I'm going to have 20 neutrons. This element here, X, has obviously 20 neutrons. That's what we're talking about. Now, write the electron configuration of X. Now, it's important to mention here in an atom here, the number of electrons here, the number of electrons here is equal to the number of protons. Let's look at that. Is equal to the number of protons. That means here that the number of electrons in this particular case here will be equal to 17 electrons. Therefore 17 electrons. So let's write the electron configuration of X. We have said here, so the electron configuration here will be as follows here. Of course, the first energy level here holds 2 electrons, and therefore I'm going to have 2 in the first energy level. Then the second energy level holds 8 electrons. I'm going to have 8. If you sum this, I have 10, and therefore 7 remains. 7 remains. And therefore, the 7 of here will occupy the third energy level. And therefore, that will be the electron configuration of X. That will be the electron configuration of my X. So basically, this is what we're talking about as far as our representation of an atom is. We need to understand each of these values so that if a question comes, we are able to handle it. That's what we are actually talking about. Now, very fast, let me take you through the isotopes. Now, let me take you through the isotopes. Now, isotopes are the atoms of the same element having the same number of protons. In other words, the atomic numbers are the same, but a different number of neutrons. Now, the different number of neutrons here, whenever the neutrons are different, remember we just said that atomic mass or the mass number is equal to the sum of protons and neutrons. That means that when neutrons changes, the mass number also changes. And therefore, another definition of isotopes may be atoms of the same element, having the same atomic number, but different mass number. That's what we are talking about. Now, and therefore, maybe let's think about maybe a cell representation that may actually tell you here that indeed those are isotopes. Now, think about, for example, something like hydrogen. Hydrogen have a number of isotopes. One of them has a mass number of 1. Sorry, this is look at that. A mass number of 1 and an atomic number of 1. What does that mean? How many neutrons do we find in this hydrogen 1? Now, and mostly, by the way, when we are presenting these isotopes, we are going to have them, for example, that way there. For example, we're going to have hydrogen 1. Look at that. We can have hydrogen 2, where the mass number now will be 2. The atomic number, as usual, is 1, and so on and so forth. I can also have hydrogen 3. 3, 1, and I'm going to have hydrogen. Look at this here. This is what I'm talking about. These are isotopes. These are isotopes. You realize here that the atomic numbers here will be the same. I'm talking about 1, 1, 1, 1. These are atomic numbers. These are atomic numbers. These are atomic numbers. They are the same. But when you get to the mass numbers, the mass numbers are different. In the first isotope has a mass number of 1. The second has a number of a mass number of 2. This is deuterium, and this one is tritium here with a mass number of 3. These are isotopes. These are actually isotopes. That's what we're talking about. And some other maybe examples that we can also give here. We can give an examples of oxygen. Oxygen here. We can have oxygen 16. We can have 17 and oxygen 18. These are actually isotopes of oxygen. These are isotopes of oxygen. The oxygen 16 eventually will have a mass number of 16. We'll have a mass number of 16, and the atomic number is 8, and therefore that will be the representation. That will be the presentation here. Now talk about the oxygen 17 here. The oxygen 17, on the other hand, here has a mass number of 17. A mass number of 17. Therefore, I'm going to have 17 here. The atomic number remains the same, and then I'm going to present it that way there. You can look at that. That will be the oxygen 17. Isotope oxygen 17 here. I'm also going to have another isotope of oxygen here. 18. Oxygen 18 here. Oxygen 18 isotope. Again, having a mass number of 18. The atomic number is the same, and I'm going to have my chemical symbol of oxygen, which is O. That's how we are going to represent them. That's how we are going to represent them. Now, if you talk about something like mass number, if you're going to talk of something like the mass numbers, when I talk about an element with different mass numbers, then to be able actually to tell, or because I may not be able to work with more than one mass number. So what can happen here is, if I'm given the abundances, the percentage abundance, that is, for example, the percentage of these 3 isotopes of oxygen. For example, this one, the 16 here is the most common here, may have, for example, 80, and the other 2 here complies or maybe composes the other 20%. If I'm given this percentage abundances, or I'm given the ratio in which these 3 isotopes exist, then I can be able to work out the average mass. I can be able to get the average mass of, or atomic mass of these isotopes. Now this one here is what we can maybe refer to as the atomic mass of that particular element here, by trying to work out the average mass of an atom, the average mass of an atom. So let me take you through what we call, or how we can be able to find the relative atomic mass of a substance, the relative atomic mass of an element which has isotopes. In other words, it has different atoms, or atoms of different mass numbers but the same atomic numbers. Now, let us again discuss maybe something about the relative atomic mass of an element. And more so, we look at the relative atomic mass of an element with isotopes. Now, the relative atomic mass of an element is the mass of its atom. The mass of its atom compared to 1/12 of a carbon-12 atom. Maybe it's important to mention here that once the hydrogen was used, the hydrogen was used here, where I would take the atoms of other elements and compare them with the hydrogen atom. Why was hydrogen atom used? Because the hydrogen atom actually is the lightest atom. It is the lightest atom. But for some reasons here, that maybe I'll be explaining later here, is that the carbon-12 replaced the hydrogen. Now this carbon-12 here is actually 12 times heavier than hydrogen. It is 12 times heavier than hydrogen, and therefore it was actually given a relative atomic mass of 12, because it's still 12 times heavier than the lightest atom here, which actually happens to be oxygen. And therefore, when it is being used here, when it is being used as a reference atom to compare the masses of other elements, the other elements here, we are going to work the relative atomic mass of an element from the atom, the mass of an atom, divided by, so relative atomic mass here, we can just have it here, will be equal to mass of an atom. Mass of an atom here of that element, we divide by 1 over 12 of the mass of carbon-12. The 1 over 12 of mass of carbon-12 atom. Now this one is actually the mass numbers. Now, so for me, these are the relative atomic mass. Now, it's important maybe to mention here that there is some, when we talk about the relative atomic mass here, there is some relationship here with the mass numbers, simply because if you try to look at maybe the hydrogen, which was actually used to measure this, was the hydrogen 1 with a mass number of 1. And when we talk about the mass number of 1 here, this one is a hydrogen here which has only one proton. Therefore, maybe you can also be able to estimate maybe here that maybe an atom here will weigh, not an atom, but a proton may be given a relative atomic mass unit of 1. And so with the mass number and the relative atomic mass here, it is almost the same. Now, let us now think about a scenario here where the relative atomic masses, or the mass numbers are different. Now, if the mass numbers are different, or the relative atomic masses of different atoms are different, I mean, if, for example, we have isotopes, which actually have different mass numbers, how do we get the relative atomic mass of such an element? That is what we are talking about. Now, I want us to give, maybe, for example, maybe think of a case here of 2 isotopes of chlorine. These 2 isotopes, for example, of chlorine, we have 37 here. I'm just going to represent them, and 17. This is one of the isotopes of chlorine here. I'm also going to have another isotope, which is 35, 17, and chlorine there. Now, if I have these 2 isotopes, look at this, for example. This first one here, the relative atomic mass of this one here is 37. Or maybe I can mention about the mass number is actually 37. Now, then the other one here has a mass number of 35. Now, how do we find the relative atomic mass of such an element? In other words, if maybe you ask me, for example, a chlorine atom will weigh how many times heavier than 1 over 12 of the mass of carbon-12 atom? Now, to be able to work out this here, we try and come up, or we try and work out the average mass. But of course, maybe to be able to work out that here, we may have what we call the relative abundances. Or what we call the percentage abundances of these isotopes. Now, think about this. In a given sample of chlorine here, by the way, there is an instrument that we can be able to use to measure the relative abundances of elements. We call it spectrometer. Now, we maybe have this kind of value. For example, the 35 here we have something like, for example, 25%. Think about that. From spectrometer here, we're able to tell that in a given sample of chlorine, the chlorine 37 has a percentage abundance of 25%, while that of chlorine 35 here will have a percentage abundance of 75%. 75%. Think about that. Now, to be able to work out the RAM of chlorine, assuming that these are the only isotopes of chlorine, how are we going to work it out? How are we going to work it out? Now, to be able to work out this one here, we need to get the average mass. We need to get the average mass of a chlorine atom. How do we work it out? Now, assuming that I actually have 100 atoms of chlorine. Assuming that I have 100 atoms of this chlorine, that means that 25 of them will be 37, will be chlorine 37. And therefore, the total mass of the 25 atoms of chlorine here will be 25. I multiply by the mass number, which is 37. That is the atomic mass of one chlorine atom. Now, let's also think about the other scenario. Now, out of 100 atoms, atoms here, 75% will be that of that chlorine 35, and that means that 37% of 100 is 75 atoms. Therefore, I'm going to have 75 atoms. And with the 75 atoms here, the mass number is 35. Therefore, I'm going to multiply by 35. Look at that. I'm going to have 35 there. And then the total number of atoms. The total number of atoms here, I've just said, I've worked with 100. I've worked with 100. Where this one here is 25, this one is 75, and therefore 25 plus 75 gives me 100. Now, if you try to work out this one here, if you're going to try and work out that one there, you'll be able to get. So I'm going to have 25. The 75 times 35. Now I'm going to have 35.5. 35.5. Now this one is actually the relative atomic mass of my chlorine. This is actually the atomic mass of the relative atomic mass of my chlorine. So basically that is what we are actually talking about as far as the relative atomic masses are concerned. Maybe we can have maybe another example. This time we can try to use instead of maybe percentage, I use the ratio. Now let's have a look at maybe the other case where I'm going to use the ratios. I'm going to use the ratios. I've just said here that these ratios may be gotten from an instrument called spectrometer. Now in this particular case here, I'm having an element W. I've just used any W by just presented element, but with the mass numbers, or atomic mass of 71 and 69 respectively. Now, if you're given that the ratio is 2:3, find the relative atomic mass of W. Now, how are we going to work out this? Now, let us try and argue out this ratio here. Now, a ratio of 2:3 means that if I'm going to have 5 atoms, of W, that means that two of them here, of course, this should be, these one 2 represent W71 and 3 represent the W69. Now, if I'm going to have 5 atoms of W here, that means that the two of them here will have an atomic mass of 71, and therefore their total mass will be 71 times 2, and then 3 of the 5 will have an atomic mass of 69, and therefore to get the average mass of each of these atoms here, I'm going to divide by the total number of atoms, which is actually 5. which is actually 5. That is 2 plus 3 here. There were 5. I'm talking about 5 atoms. Now, working on this one here, let's see what you get here. You'll get you'll get 349 divided by 5. 349 divided by 5 here, and you actually get this one as 69.8. 69.8. Look at that. 69.8. Now, one thing that maybe I can mention about the relative atomic mass of this kind of elements with more than one isotopes, or maybe with the isotopes, is that if you try to look at, for example, the 2 here, if this one here you convert it maybe to percentage, this will be 3 over 5. 3 over 5 times 100. 3 over 5 times 100, that's 60%. So 69 here, you realize it is 60% of the atoms will have a mass number of 69, or atomic mass of 69. That will mean also, when it comes to the relative atomic mass, when it comes to the relative atomic mass, you realize the relative atomic mass here will be closer to 69. Because the relative abundance, the percentage abundance, or the relative abundance of W is actually more compared to W. That's what we're talking about. And I think that one there marks the end of my lesson 2. That marks the end of my lesson 2 on atomic structure and periodic table. In my that lesson, I will be taking you now through the periodic table. I'll be taking you through the periodic table. So kindly, let us give comments, let us subscribe, let us like,